Okay, so let's look at the response of this standard second order system with transfer function omega n squared over s squared plus 2 zeta omega n s plus omega n squared. Now, we'll assume that omega n is positive. We may wish to consider the case where zeta is 0, so let's just say for now that zeta is non-negative. Examples of systems with this transfer function are, as we've seen, the cruise control under integral control, a mass spring damper example, or an RLC circuit. As we said in the previous video, this parameter zeta is called the damping ratio and omega n the natural frequency. That terminology, in a sense, comes from the mass spring damper example. So suppose we wish to compute the responses of this system. Well, we're going to want to do some partial fractions expansion, so we're going to want to find the poles of the transfer function, that is the roots of the denominator. So given that the denominator is a quadratic, say with coefficients a, b, and c, we know that the roots lie at minus b over 2 plus or minus 1/2 b squared minus 4ac, or in other words, b over 2 squared minus 4ac. A in this case is 1, so what we get in this example is minus zeta omega n plus or minus the square root of zeta squared omega n squared minus omega n squared. Now, the question that arises immediately is, do we have real poles or actually complex poles with non-zero imaginary parts? That's obviously going to depend on the sign of the term under the square root, the discriminant, if you like. So in this case, it's going to depend on the value of zeta. If zeta is greater than 1, then this is going to be a positive quantity under the square root sign, so we'll have two real roots. And in fact, if zeta is strictly greater than 1, then those poles are going to be distinct. So in fact, if we do a partial fractions decomposition, we can do a partial fractions decomposition of the transfer function itself and decompose it into two standard first order systems. Into the transfer functions of two standard first order systems. So we can use the results we found last week, for the impulse response and the step response of the standard first order system. We'll essentially have two such systems in parallel if we have the sum of two such transfer functions. So we'll just have to find their responses and add them up. So this case, where zeta is greater than 1, reduces to the case of the first order system. If zeta equals 1, then we have a repeated pole. If zeta equals 1, the term under the square root sign is 0. So we have two poles at s equals minus zeta omega n. Okay, so that means in this case, by our T multiplication property of the Laplace transform, what we have is a decaying exponential multiplied by t for our impulse response. And they'll ask you to check this. Okay. So this is a bit of a special case, of course. This is what's referred to typically as the critically damped case. So it's slightly different from the kind of responses you get with the first order system, but in a sense, not a whole lot. Where you really get different responses, and there's a sneak preview of them, is within the so-called underdamped case. And this is what we're going to concentrate on. This is the case where zeta lies between 0 and 1, and let's say that's strictly positive and strictly less than 1. In this case, of course, the term under the square root sign is negative. So if we look at our expression for the poles, we have the first term minus zeta omega n becomes the real part, and the poles themselves the imaginary part, plus or minus omega n times the square root of 1 minus zeta squared. So we have complex poles in this case. So this gives us something really different from the first order case where, of course, we could only get real poles. So we can find the impulse response in this case. Of course, the impulse response is just going to be the inverse transform of the transfer function itself. So what we can do, in this case, our transfer function is omega n squared over s squared plus 2 zeta omega n s plus omega n squared. So what we can do is do a completion of the square. Okay. Then we'll take s plus zeta omega n squared to give us the first two terms in our quadratic, and then we'll have to subtract zeta squared omega n squared. So we'll end up with omega n squared over s plus zeta omega n squared plus omega n times the square root of 1 minus zeta squared. You may already recognize some of these terms. Minus zeta omega n is the real part of the poles, and plus or minus omega n times the square root of 1 minus zeta squared is the imaginary part. And what this gives us, well, we know that if we just had s squared here, this would be the transform, roughly speaking, of a sinusoid. We'd need another square root of 1 minus zeta squared up here. So we'll divide by the square root of 1 minus zeta squared, and that will give us essentially the sine of omega n times the square root of 1 minus zeta squared, except it will be multiplied by e to the minus zeta omega n by the exponential modulation property of the Laplace transform. So what we get is e to the minus zeta omega n t times the sine of omega n times the square root of 1 minus zeta squared times t. So we get a damped sinusoid, if you like. The impulse response gives us sinusoidal oscillations whose amplitude decays exponentially according to this real exponential here. If you compute the step response, go through the exercise of computing the step response, taking the inverse Laplace transform of h of s times 1 over s, the transform of a unit step, what you will get is 1 minus 1 over the square root of 1 minus zeta squared times e to the minus zeta omega nt. Better move this. Times the sine of omega n times the square root of 1 minus zeta squared t plus theta, where theta is the arc cos or the inverse cos of zeta. And of course, as we saw in general, this transform here, h of s times 1 over s, it's obviously the transform of the step response, but it's also the transform of the integral of the impulse response. So in general, the step response is the integral of the impulse response. So this is the integral of the damped sinusoid that we just saw. So what do these responses look like? Well, here we have some plots of them. Now again, there are two parameters involved, zeta and omega n. We have in fact plotted these responses as functions not of t but of omega nt, because if we go back and look at the expressions for the two responses, in both cases, everywhere we see t, it's multiplied by omega n. Whether we look at the impulse response or the step response. So instead of plotting them versus t, we'll plot them as functions of omega n t. And then, of course, we'll get different responses for different values of zeta. When we look at both of these, obviously they're going to have similar characteristics since one is the integral of the other. The smaller the value of zeta, which we call the damping ratio, well, the less damping there is of our damped sinusoids, and the larger their amplitudes and the longer their amplitudes take to decay. So here we've plotted the case of zeta equals 0.1 and zeta equals 0.25. As zeta gets bigger, the amplitudes die out faster. This case, zeta equals 1, is again what we call the critically damped case. So in this case, the impulse response has the form of a decaying exponential multiplied by t. That's what you get when the roots are repeated. They're both at minus zeta omega n. But we're concentrating on the underdamped case here. So we get these damped oscillations. And the larger zeta, the more damping there is. On the other hand, omega n determines the frequency of these oscillations. We know that their angular frequency is actually omega n times the square root of 1 minus zeta squared. Again, it's natural to plot these as functions of omega n times t, so that tells us that in a sense omega n also functions as a sort of time scale. It determines the time scale. For instance, we've plotted here omega nt from 0 to 10. So if omega n, the so-called natural frequency, is 1, it takes us 10 seconds to get to this point. If omega n is 10, on the other hand, it takes us only 10 radians per second. It takes us only 1 second to get to this point. So you can think of this parameter omega n as determining the speed at which the response occurs. Zeta, again, determines the amount of damping of our damped sinusoids. When you look at the step response, you get this sort of plot. Again, we noted that the DC gain of the transfer function is 1. That means the final value of the step response is 1. And in fact, the first term in our expression for the step response was that 1. So apart from this 1, we just have this term, which is itself a damped sinusoid that will decay to 0, leaving 1 as the steady state value of the response. Other than that, we can observe the same sort of thing that we did about the impulse response. As zeta gets larger, these sinusoidal oscillations get damped out faster. Here again is the critically damped case where zeta equals 1. And again, omega n determines the speed of the response. This is the point where omega n t equals 10. So if omega n is 1 radian per second, it takes 10 seconds to get to this point. If omega n is 10 radians per second, it takes only 1 second. So for our cruise control example, we would probably arrange to have an underdamped response. That's quite typical for the responses of control systems. What kinds of things are we going to try to specify if we actually write out specifications for the cruise control? We would ideally like the system to settle down reasonably quickly to reach its steady state value, or to get close to its steady state value reasonably quickly. That probably means we're going to want omega n to be sufficiently large, but we're not going to want a lot of crazy oscillations of the speed. We may accept a little bit of overshoot of the steady state value in order to get close to the desired steady state value quickly. But we won't want a lot of big oscillations that take a long time to die out. So we won't want zeta to be very small, like 0.1, maybe 0.4, probably a bit bigger even than 0.4. What does this correspond to? Well, we said at the outset that a big part of the exercise in this part of the course is to relate the form of the response to the positions of the poles. Because we saw, in fact, in our example of proportional control with the cruise control system, that by adding this feedback controller, we can effectively shift the poles around on the S-plane. So we want to know where to put the poles in order to get a nice response. So we need to know the relationship between the locations of the poles and the form of the response. So let's plot the pole locations, specifically for this underdamped case. So we know that in this case we get complex poles, and specifically their real part is minus zeta omega n. The imaginary part is plus or minus omega n times the square root of 1 minus zeta squared. Okay, so we saw these terms crop up in our expressions for the responses, both impulse and step responses. So looking first at the impulse response, again, this minus zeta omega n is simply the real part of the poles. So the real part of the poles shows up in this real exponential that determines the rate at which the oscillations are damped. That's the real part of the poles right there. And this omega n times the square root of 1 minus zeta squared, the angular frequency of the sinusoidal oscillations, is exactly the imaginary part of the poles. So the real part determines the rate at which the oscillations decay. The imaginary part determines the angular frequency of those oscillations. And of course, that's true of the step response as well, since the step response is just the integral of the impulse response. Here's that e to the minus zeta omega nt, which decays at a rate according to the real part of the pole, minus zeta omega n. Here are our sinusoidal oscillations in this case. And they have an angular frequency of omega n times the square root of 1 minus zeta squared. So that's one way of relating the locations of the poles to the form of the response that we get. The real part determines the rate at which the oscillations decay, the imaginary part the frequency of those oscillations. But there are other ways we can relate these two parameters, zeta and omega n, to the locations of the poles. Note that this real part is minus zeta omega n. The complex part is omega n times the square root of 1 minus zeta squared. If we take the sum of the squares of those two components, we're going to get omega n squared. Take its square root and you get omega n. So what that tells us is that omega n is this distance here from the origin to the poles. In other words, it's the modulus of the poles. Now, if this distance is omega n from the origin to the poles, and the real part of the poles is zeta omega n, then zeta must be the cosine of this angle. So this is the angle theta that we referred to in our expression for the step response. This is the angle whose cosine is zeta. So that's another way of relating the responses to the locations of the poles. Now again, we know that omega n can be thought of as a timescale factor. The larger omega n is, the faster the response occurs. And we saw that the larger zeta is, the more damping there is. Now with zeta, we have to think of zeta, if you like, as the cosine of the angle theta. So if the cosine is getting bigger, that means the angle theta is getting smaller. So if zeta goes up, theta goes down, and we know that we get more damping, if you like. The sinusoidal oscillations are damped faster. So there we have essentially two ways of relating the pole locations to the responses. Once again, we saw that the imaginary part of the poles is the angular frequency of the sinusoidal oscillations. And the real part, e to the minus zeta omega nt, determines the rate at which the oscillations decay. So you can look at things either in terms of the real and imaginary parts of the poles, or in terms of the modulus of the poles, omega n, which is equal to omega n, or this angle theta, which is the arc cos of the damping ratio zeta. So again, I said that in designing our control system, or with integral control, normally we would go for an underdamped response. So we would have complex valued poles like this. And then we would try to choose the value omega n that would give us a good speed of response, one that would get us near to the steady state value 1 reasonably quickly, but not too quickly so that we subject the passengers to high acceleration or a large jerk, which is the rate of change of acceleration. We would also not want the system to go on oscillating too much or to overshoot the steady state value by very much. So that means we would not want zeta to be too small. In other words, we would not want this angle theta to be too large. We would want that angle theta to be small enough that we didn't get a lot of overshoot or long-lasting oscillations. And this is the sort of game that you play when you design control systems, and you'll see much more of this in SE380, where the real game will be to shift poles around on the S-plane. Okay, in the next video then, we'll quickly return to our cruise control example for this case of integral control and relate it to this analysis that we've just done of the pole locations in the underdamped case. See you there.